All right, everyone. Welcome to the second lecture in celestial holography. Before we start, I would just like to remind everyone that the recording for the first lecture is already available on our YouTube channel, and also the lecture notes are already available on the website. So check them out if you haven't already. So Agata will start the second lecture. Agata, the floor is yours.
Okay, so the second lecture, and let me do a brief review of what we are going to do in the second lecture, or at least what would be great if we had, if we would do. Firstly, I will spend, I think, maybe 20 minutes or a little bit less talking about the correspondence between SO13, so Lorentz, and SL2C, so global conformal algebras. We will set the correspondence on the level of generators. And we will, as I promised, we will return to the picture of Millennium Falcon and talk a little bit about how this correspondence of two algebras is related to this picture. And then we will set our finally dictionary. We will talk about which wave functions will we use in celestial holography, how are they related to plane waves, and in the massive case, in the massless case. And then the last thing, if we have time, we will also see the first example of celestial amplitude, how it looks like, and how it should be treated. Okay, so with this being said, again, I will share my lecture notes shortly after the lecture, and maybe there will be a little bit more details than in what I will perform here on the board. But it will not be like 15 pages like the first lecture, which I hope you guys looked through. It will be just a little bit of extension of what I'm going to say today. Okay, so we start with the following paragraph. Lorentz algebra, and SL2C algebra. So algebra of Witt or Virasoro generators. First of all, we will remember that our Lorentz generators, they can be written down as orbital angular momentum generator plus the spin part, right? And for our purposes, we will mostly disregard the spin part. So this is the orbital angular momentum generator. This is the spin part. Spin generator, we will disregard this one. We will consider the scalar case because it's easy, because our course is called Welcome to Celestial Holography and not deep down in celestial holography. And this will just give us the understanding of intuition behind all the story. So yeah, reminder that our orbital momentum have the following form: x mu d mu minus x nu d mu, right? And it can be split in two parts in rotations ji and boosts ki. So rotations are in general written down as the following: generators xj, k, and boosts are x 0 di minus plus xi d0. These are our Lorentz transformations, 6 of each, right? I, j, and k is the space indices. Yeah, 1, 2, 3. Okay, great. And in our standard Cartesian coordinates, the Lorentz algebra commutation relations are just simply ji, jj, epsilon I, jk, jk. Then the boosts commute in the similar manner. No, there is no difference between up and down indices in this case. Let me open the chat. Yeah, because it's just SO3 indices, they can be treated wherever, in the top, in the bottom, wherever you want, right? So E minus ijk, jk, and boosts with rotations, they have the following relation: epsilon ijk, k. Okay, this is our commutation relations. So far, they do not remind us yet the SL to C commutation relations at all, right? Remember where it was, where we were written the algebra, right? Doesn't remind us anything like that. I mean, a little bit, but commutation relations. Okay, great. Now we will introduce the new coordinate system. And in details, this is something that I will not talk a lot about, of how we parameterize the Minkowski space. That was previously, we had the metric, we had the coordinate system, just the Cartesian coordinate system, minus d tau squared, no, sorry, minus dx squared, plus dx1 squared, plus dx2 squared, plus dx3 squared. And then we go to a different coordinate system where metric looks like this: minus d tau squared plus t squared d rho over rho squared. And you can see the more complete analysis and with pictures and some figures. You will see it in my notes. For now, for me, it's enough just that we made the coordinate change. And we will, with a coordinate map. And for me, it's important to state here that the celestial sphere will be obtained, the celestial sphere limit in these coordinates. Limit will be obtained when we take plus minus tau to be infinity and rho to be infinity. So this is, we will obtain the celestial sphere of the future and the celestial sphere of the past. And in this, if we firstly introduce these coordinates, I can write down the formulas for connecting our Cartesian coordinates and these coordinates if you want. Do you want? Or will it be helpful for you? No? Okay. Maybe because it's not. Okay, anyway, I will write it down just because maybe.
Yeah, I think it is useful.
Yeah, okay. Okay, so how they will be connected in the following manner: plus z bar plus rho minus 2, 1, 1, 2, tau rho z bar, and x squared minus I over 2 tau rho z minus z bar, x3 1 tau r 1 minus z bar minus rho minus 2. Okay, and so again, the celestial sphere we will obtain when we take such a limit. Place it a little bit below. So what will happen when we change coordinates like this and substitute it in our Lorentz algebra generators? What will happen? How they will look like? So when we substitute these coordinates and then take the limit of tau and rho to infinities, we will obtain, will arrive to the following form of Lorentz generators. First will be minus I over 2 z squared minus 1 dz. Right here, nothing already depends on tau, neither on rho, because the limit is taken. They are infinities. Then J2 is 1 over 2 z squared minus plus 1 dz minus plus z bar squared plus 1 dz bar, and J3 is minus I z dz bar minus z dt bar. And these are our rotations. As you can see here, we in this coordinate system, we basically made the coordinate 3 special. So the rotations, and also we'll see now the boosts in the third direction, have very nice form. And while I'm writing down the expression for the boosts, you can think about the question, what does this remind you? If it does remind you something. So boosts are written in the following manner. dz bar k2 not minus, I over 2 z squared plus 1 dz minus z bar squared plus 1 dz bar, and k3 is also z dz plus z bar dz bar. So now, with all of these things written down, I will even put them in a box. These things already should remind you something. Remember when we were writing down the, not here, no, here, the generators of SL to C global conformal transformations. Remember, how does L minus 1 looks like? L minus 1 is minus D, right? L0 is nothing but minus Z dz. And L1 is nothing else but minus z squared dz. And the following analogous thing about the L bars. So this is our SL to C subalgebra of weak algebra. And yesterday, I believe I mentioned it in I mentioned it by words, but I didn't write it down. That these are our translations. These are dilatations. Dilatations plus rotations. And these are special conformal transformations. Remember the inversion plus translation plus inversion again. So this thing here is nothing else but dilatations or rotations, but when we write down the sum of L plus L0, it will be minus Z D minus Z bar D bar. This will be nothing but just pure dilatations. And what we have here in our Lorentz generators is just combinations of these three generators. You can see, right? There is nothing else but just derivatives, partial derivatives, and partial derivatives together with z squared, or partial derivatives together with z. So it's something inside, it's some combinations of L1, L0, and L minus 1. And this is how we set the equivalence between Lorentz algebra and weak algebra on our infinity of the Minkowski spacetime. So when we write down this explicitly, we will just, for example, the L0 is given by I/2 third boost plus third rotation plus third boost, and the L0 bar is I/2 third rotation minus third boost. Then we have L1, which is the I/2 J1 plus AK1 plus AJ2 plus AK2, and the corresponding L1 bar. I will not write it down. You can just basically conjugate this expression here. It's an exercise. And the L minus 1. Write it down. K1 minus sign J2 plus sign K2. And I have L minus 1 part also. So yeah, as you can see, for example, the boost in the third direction is nothing else but the sum of two of L0 and I see the question. So the correspondence is a coordinate transformation in some sense. Yeah, I'm showing it using the coordinate transformation, but for example, if you are familiar with the spinor helicity formalism, it's even more clear in the spinor helicity coordinates. It's a formalism that's used broadly in amplitudes when calculating amplitudes. But here I just didn't want to overload the material with another yet formalism. So I just went to this together with the coordinate transformations because I think it's a little bit easier to see like this without any additional requirements. But it's not just because of the coordinate change. It's the property of this Minkowski spacetime itself and its symmetries. The Lorentz group is isomorphic to it's actually for people, for very rigorous people, SL2C is a double covering of the Lorentz group. And yeah, so we can see that we restored our two copies of SL2C generators here from the Lorentz transformations. And that's an important, I think, part to also be mentioned in the celestial holography frame because, well, now let's return to the very beginning of our lectures where there is a Millennium Falcon and Han Solo with Chewbacca enjoying the ride. So in the movie, we see that when they are accelerating and then moving with the speeds near of the speed of light. So first they were in the racing frame, and then they somehow accelerate and become inside a frame of a very fast moving observer. So what happens during these transformations, as it shows in the movie, is that first the stars were around them, and then just like inside the rain or in the snow, they start moving towards them. This is not really what actually would happen because when we write down, for example, actually maybe we can write down already here under the picture. So when we, for example, when an observer has at a racing frame, it sees a star on an angle theta, and then it starts moving towards the star, and the and the angle becomes theta prime. These angles will be related by the following relation, that the tangents of the primed angle is 1 minus v. Here, speed of light is 1. And the tangences are related in the following manner. When we go to our stereographic coordinates, to our coordinate net, stereographic coordinate net, and do the transformation, right? Is a tangents of theta halved, and the phi exponent of the I phi, and the same, but with minus in the exponent, goes to z bar. We will see that z and the z bar transforms as following: z prime, the new z prime, and the new z prime bar on our sphere, they transform as following. So what they see analyzing this factor here, we can see that this factor is less than 1. So and we remember that our coordinate net is such that the direction of our movement is the coordinate 0, 0, 0, right? So z bar 0, 0 points at the direction of movement. So when when we make a Lorentz transformation, the stars that we see, they are not moving back, like hugging us around. They are actually concentrated around the north pole of our celestial sphere. So when we are moving towards some direction, the stars will be concentrated around there. And then we can also talk about the Doppler effect, but that's not my point. My point is that the way that the stars were transformed is just a dilatation on the celestial sphere. So basically the distances, if we project this sphere on a surface, right, as we do in the projecting plane, we will receive just the normal dilatation, just the dilatations of our vectors. So basically, what properly should be here is that they are moving forwards and stars are on the opposite, not moving there, but moving towards them. That's what they will see. This is what I wanted to say. I think this picture is nice for celestial holography purposes. Yeah. So I hope it was more or less clear. And now how come boost and rotation seem to be related? Are they? I don't see this. If you, there is minus, see, there is plus and there is minus. If we just multiply by I, there will still be plus. Okay. Okay. All right. Now there is no there will be no funny pictures up to the end of the lecture, but there will be a very important dictionary for our celestial holographic dictionary. So let's move to the conformal primary wave functions. So we need somehow to describe processes using our holographic description, right? We need to describe processes that happened on celestial sphere. And this means we need to somehow relate our bases inside the four-dimensional bulk and four-dimensional boundary. So what do we impose on the wave functions that should be our building bricks of the theory? We impose, first of all, we will consider again the only scalar case. We will not talk about spins at all. So first of all, these functions are conformal and primary, right? This means that they should obey the highest weight condition. So our functions should be annihilated by the lowering operator. Zero. And then also they should transform as primaries. under the symmetry transformations. And the second is that they are wave functions, which means that they should obey the wave equation, right? Wave equation, which we will take as just the Klein-Gordon equation. Let's see. And this is what we will deal with today. So the notice that a wave function with a weight that is proportional to the following expression plus x3, it obeys the highest weight condition. So notice that such function, it obeys the condition L1 equals L1 bar equals to 0. It satisfies the condition and also the boosts in the third direction, which we just derived, that the boost in the third direction is a combination of the L0 and L0 bar. This function diagonalizes the boosts in the third direction, direction of x3, right? And L0 minus L0 bar is 0. So a function that has something like this in the denominator would be good for us. But unfortunately, that's not the end, because we still can take something like, if we consider the f delta as something in the numerator proportional to the length of the x of the vector, and in the numerator it will be still this x0 plus x3, which we will write down in a more compact form. Here we will just use the vector q, which is 1, 0, 0, 1. So when we take the scalar product of any vector with this q, it will give us nothing else but this sum of first 0 and third component. So if we consider function scaled by this function, if we consider a wave function with a factor of some f depending on the length of the vector, it will still satisfy all the three conditions. Will still satisfy, let's denote it as star. It will still satisfy them. So yeah, it's a good conditions, but it's not enough to fix the form of the wave function. And to fix the form of the wave function, we will impose the wave equation. So to fix this f, we will impose wave equation. And then we will obtain the differential equation on f, and we will solve it. And you can see it in more details. I did it in my lecture notes. I will share them again after the lecture. But if we solve this equation on f, we will arrive to the following. Then, after solving solving it with respect to f, we obtain the form of a wave function up to some normalization constant that will look as following. Here is the x squared. Here, please don't confuse this x squared with the second component of the coordinate vector. This, I mean, x mu here. Minus 1 over the q times x times the Bessel function of the second kind, or first, I think, yeah, the second kind, yeah. Bessel function of the second kind. This will be the answer for our differential equation that we obtained from the wave equation. And it's nice, this function, because we can check that under Lorentz transformations, for example, Q transforms as follows: dz bar over dz, no, dz prime, sorry, dz prime over dz times the transformed vector, and the vector x mu is just the mu x mu. From here, we can easily derive that the wave function itself transforms as a primary, which is very good for us to check. So what we obtained is the following expression. Here again, here can be some constant. Normalization is a different story, not very important for us right now. But the function should have the following form, right? It transforms as a primary. Remember, the primary, where is it? No, here. Yeah, the primary transforms as following. Here we don't have a spin, so just scaling dimension delta survives for our wave function. Okay. Well, that's all very good, but honestly, nobody likes just leaving some hypergeometry, some Bessel functions in the answer. So very important for us to write this down in the integral representation. Let me explain what I mean. Integral representation of our wave function, wave functions. So the wave function, depending on the x and z, is actually integral over a hyperboloid, three-dimensional hyperboloid with some integral measure that I will explain below. With the weight, so the integral is weighted over the bulk-to-boundary propagator, which I will also explain in a couple of seconds. And here we have just the transformation of plane wave. So what we just wrote, it's basically a Fourier expansion on plane waves. And let me write down now all these notations, the notations that I wrote. So the integral measure is a SO13 invariant measure that is given by, let me rearrange. So 1,3 invariant measure, so Lorentz invariant measure given by the following expression. The integral over hyperboloid from 0 to infinity dy over y in the third power of 3 and times some two-dimensional vector. Here, the parameterization of our normal four momenta is connected with the three coordinates as follows. 1 plus y plus y plus w, w bar, w plus w bar, minus I, w minus w bar, and 1 minus y minus y squared minus w bar. Notice that from the four momentum, we arrived to just three components, right? Y, w bar, because we are already fixing that we are on a massive shell. So this vector here already has the mass, and it's here, and this is our parameterization of momentum. There was a question or not? I don't know. I just saw the.
There is a question. There is a question. What is the H3 set?
It's the three-dimensional hyperboloid. Basically, this is the hyperboloid where our momentum is parameterized. So the massive momentum is parameterized by these two variables w bar that are basically, if you slice the hyperboloid, this will be the coordinates on this slice, and then there is y, which is the radius of hyperboloid. And yeah, that's it, something like this. I will include the little picture of the hyperboloid if I find a nice one in my lectures. Okay, so this is from now on, we will live in this parameterization of massive momenta. About massless limit, we will talk in a couple of minutes. But if you want to work in celestial holography, then and if we want to calculate some amplitudes, we need to get used using this coordinate system. Okay, all the integrals will be with such a measure. Okay, the measure understood. Now let's understand what is bulk to boundary propagator. I mean, we will not understand what it is. I will just claim this is the expression for bulk to boundary propagator. And this is a function. this is a function y over y squared plus z z minus w squared in the conformal dimension with the scaling dimension. Here, notice that I hide it inside the P, I hide the dependence on Y and two components of W, okay? So the propagator depends on basically five variables, right? These variables are two-dimensional. Okay, and I mean, it also can be written in the momentum space in the following form. Here, you know what, let me a little bit refine our notations. This will be 1 with a head, and we will say that the momentum vector is m times vector with a head. So from now on, when we usually, most of the times when we put a head on a vector, on a momentum vector, we will mean that it's mass. It doesn't have a mass dependence inside it. Okay? So the propagator in the momentum space can be written in the following manner. To understand where this comes from, I refer you to the to the paper, to Witten's paper, Anti-de Sitter Space and Holography. And yeah, that's it. For us, it's just a function, it's just a weight function with which we are integrating our wave functions here. Okay. So this is the integral representation of our wave functions. And also, I think it's important here to state maybe that the ADS3, yeah, let me write it down. This is ADS3 bulk 2 boundary propagator. This is he. Itself, it transforms as a primary. So when we do coordinate change, it transforms as a primary. Here, vectors, of course, minus delta over 2, G, and K. Okay, that's good. We found which wave functions we will use in our analysis, which are conformal primary and satisfy the Klein-Gordon equation. Important here is to consider the massless case. So if we go to the massless limit, and we go to massless limit here, okay? We will go from here because it's easier. It's easy. It will be more easier to consider the massless limit of the bulk to boundary propagator, and then just write down again the new massless wave function in integral representation. So let's say massless case. How we will take the limit? massless limit is taken by sending y from this parameterization y to 0, while leaving m over 2y as a constant, omega, which will be basically our energy of the massless particle. So if we write down the expansion of the limit of the propagator in this limit, so y to 0 over of the bulk to boundary propagator, we will get two terms and some further corrections. We will firstly obtain some term that when y is going to 0 will be totally singular in when z approaches w, or actually when w approaches z, because in here in our notation this is a coordinate on the boundary, right? The coordinate on a sphere on a boundary, and w is just the bulk parameterization of some hyperbolical parameterization, but w lives in a bulk, right? So when we approaching the boundary, while also taking limit y to 0, we will get something very singular on this boundary. So there will be a term represented by a delta function. Okay. So it will be firstly some normalization constant that is taken by integrating the propagator itself. I also performed it with details in my notes. I don't think that this is special for celestial holography computation. So first term will look like this. So here is the singularity that we pointed out, and this is just the power of y that will arise from this combination, right? Plus some power that we will find when normalizing this delta function. And the second term will be already of the following form. Z vector C minus vector W in the following power. So it's non-singular on the boundary. I mean, it's singular on the boundary, but when we take the y to 0, it's already not as singular, right? And when we now integrate, if we go to the next page, if we integrate our expression here, if we integrate this expression with the first term, let's say within 2 stars, integrate with the first term instead of the full propagator, so with the massless limit of the bulk to boundary propagator, we will obtain, and also while also taking changing the variables of integration from 0 to infinity of dy to 0 to infinity m over 2 omega squared w d omega. There is finally, this is indeed omega. This is not w, right? This omega here, that will be energy of our particle. So when we integrate our wave function with the limit of bulk to boundary, massless limit of bulk to boundary propagator, what we will get, and again, we impose some normalization, so all the bad, ugly factors in front of the integral will disappear. We will arrive to the following expression for our massless wave function. From 0 to infinity, d omega delta minus 1 e in the power of e omega q of z times x. Notice that here, right, we already integrated this part here over the delta function. So wherever there is dependence on w, for example, here there was dependence on w. After integrating over delta function, we arrive to the p dependent on z, right? So there is no variable w anymore. There is no variable y because we changed it to our non-vanishing, some fixed variable omega. And we obtained the following form for the massless wave function. So now we have the whole set of our wave functions. This one will be massless, conformal, primary wave function. This will be our massive conformal primary wave function. And well, we are all set to finally introduce some celestial amplitudes. It's not a very big part here that I wanted to say. It's already, we've been talking about for about like 50 minutes. Do you guys want me to introduce the celestial amplitude itself, or you're tired and you want to go? How are you feeling?
Are you listening to me? Uh, I
Oh,
want to make a question
um,
about the motivation to find this function, this wave function. It's like you trying to find something that works like a function that can be decomposed using plane waves, and you find the operator that do this in the boundary, and you start to study this operator because it have these properties. It's
yeah,
something like that.
yeah,
I don't know
because
if I get.
it Yeah, because it's basically we are interested in setting conformal field theory on a boundary, right? So this means that we want some fields that will behave like conformal field theory fields on this boundary. And so these fields should obey our conditions, the highest weight condition, so annihilated by the Lorentz operators, and they should transform as primaries. That's basically all motivation. But because if we don't set this dictionary properly, if we don't find the correct functions, then we will not be able to use all the CFT techniques to supposedly make our life easier when going from one basis to another. So for example, like already here you can see that in general, in our Minkowski space, when you learn special relativity, the action of, for example, boosts, right? It's a very complicated question. It's a very complicated action that you have very big matrices that act on your states, right? Transform them with respect to Lorentz group. And here, for example, Lorentz boosts are just given by this cute little form. And so this is what we expect from introducing conformal field theory on the boundary in general, that maybe something will be easier in this basis. But yeah, it's just a change of basis. It's nothing.
Yeah, I guess I got. And I was thinking that it looks a little bit like the what Penrose did using the some kind of rotation of the metric to find the principal null coordinates, like to you know.
I'm not sure I can recall it very clearly right now. But
It's like a decomposition using spinors, like so you can map the Minkowski space.
I think here is a person named Rafael in this chat that actually knows things about.
Oh, okay, okay, it's fine. It's just I was just thinking about it, but it's okay. Thank you
Yeah,
for
maybe we
the
can carry on this
explanation.
discussion after the lecture ends.
Yeah, okay. I mean, and yeah, maybe it was something that I was planning to discuss later, but maybe not. I don't know. But yeah, this is the intuition standing behind all this story. Like we just want to make our life a little bit easier. Will it become easier? That's big question, but we will try. So okay, now let me introduce the what celestial amplitude is. So it's nothing else but the, let's write definition. Okay. Definition. Celestial amplitude is a transformation of a momentum space amplitude. The following transformation. So we will denote the celestial amplitudes A with tilde, and there are some scaling dimensions. Z bar E I plus 1 and over H3. And there is all these measures for each of the fields, each of the particles. Our weight function, our propagator. Yeah, let me just keep on saying vector of z, and the original momentum space amplitude. So yeah, here this is just incoming or outgoing particle. Okay, and good news is that if we do a Lorentz transformation or of the original amplitude, and from the other side, if we do an SL2C transformation of the celestial amplitude, it will transform as a primary also, because we built it this way, just did. So will be Z bar prime vector Z prime, and the product of derivatives, right? So derivative of the coordinates, how they change it, minus over 2 A amplitude into before transformation. So yeah, and here is important to notice that the wave functions that we just built, they are not a basis for any weights delta. There is a certain restriction on the weights that these weights should satisfy. So for massive case, weights should be we should be able to represent the weights as a sum of with the real part 1 and positive imaginary part. And for massless case, it should be just any real number, this one. One can derive this by asking these functions to form an orthonormal basis, and also that they should be delta function normalized with respect to the inner product. And yeah, and then they will form a linear independent basis only for this set of scaling dimensions, weights, which are called principal continuous series. Principal continuous series. And just for us to touch these examples with celestial amplitudes, let's write down the 3-point interaction. That's the 3-point interaction, just like the vertex. How will our celestial amplitude looks like? So 3-point celestial amplitude. In momentum space, it's just the vertex, right? It's just the delta function, omega 1, q1. We here restrict ourselves to 2 massless particles plus 1 mass, and all of them are scalars. And we consider 3 level. Okay. The out is plus, maybe not. I think it depends on your notations. Sometimes people say that out are plus and in are minus, but it's important just to keep track of it during your own calculation. It's not that important to in general. You just need to be consistent with them inside your own calculation. So minus massive momentum, and then we go to the celestial basis and the integral transformation of our momentum magnitude will look as follows. So first of all, we will have two integrals, two massless integrals, right? And this with this transformation, massless transformation, I forgot to tell you that maybe you recognize here this is a Mellin transformation, Mellin transform. So it's just the integral transformations like this are called Mellin transformations. So usually when we will talk about transformation over a massless particle, we will also refer it as a Mellin transform. Okay. So we will have two Mellin transforms, the omega 1, omega 1 in the 1 minus 1. Then we have from 0 to infinity. Then we have omega 2 also. We take the integral over omega 2. And also now we have integral over our massive particle, which is parameterized by our three hyperbolic variables. 3 e squared over w. And yeah, let me transfer it here so I will not break the formula in two lines. Then we have our propagator, right? Z3, because the third particle is the massive one. So delta 3 and our delta function, right? We'll need to break the formula in, oh, maybe not. Yeah, I will try to fit it all here. Delta 1 plus omega 2 u2 minus m. Okay, when computing integrals like this, the most difficult part is finding the roots of the delta function. So once we find the roots, we can take 4 of the integrals, right? Because the delta function is 4-dimensional. So we need to find roots, and in the scalar massless case, or even in this case where there is one massive and two massless particles, it's very straightforward. But once we go to more legs of the amplitude, so not just 3-point interaction, or more massive particles, it becomes really horrible. Like it's really sometimes difficult, and the integral transformations become really not nice. But we will only talk about the nice part today and tomorrow and the day after tomorrow. So when we find the roots of the delta, and we can also firstly parameterize the massless momentum as follows: some z bar, z plus z bar. This is our massless parameterization. The massive parameterization is given by the formula that we wrote here, right? And this is our massive parameterization. And then when we find the we can evaluate 4 integrals, right? Here we have 1, 2, 3, 4, 5 integrals, and we can take 4 of them using the delta function, right? So when we find the roots of delta function and integrate over them, we will arrive to, I will not write down the details of how to solve this thing here, but we will arrive to the integral of just one variable, right? And this will be something of a form, some factor, right? Some factor not depending on our variables, then 2 minus delta 3 minus 2. Then we have the difference of z1 and z2. Remember, my notation is still the same, that is just z1 minus z2. And the rest of the integral that we will compute now, which in our 3-point function, in this case, it's very straightforward. What is this? Over m squared times z1 z1 3 squared delta. Here we remember that integral of this form is we can transform it to an integral having this form t alpha minus 1 minus t beta minus 1, and this is just a beta function, right? So it's just gamma alpha, gamma beta over gamma alpha plus beta, which is a beta function of alpha and beta. So when we finally evaluate the last integral, we will arrive to the following expression for our celestial amplitude. There will be some numerical factor inside this factor. There will sit as well our beta function will be inside of it. So there will be beta of gamma of delta 1 2 plus 1 3 over 2 and minus delta 1 2 plus 3 over 2 is somewhere inside, also with the mass and with the coupling constant. And next we have the following very familiar already, I hope, to us expression. Plus delta 3 minus delta 2 and z. 2, 3. Delta 2 plus delta 3 minus delta 1. Well, and now we can clearly see that this is nothing else but one of the 3-point functions that we were talking about yesterday in the CFT course. So this 3-point function, it indeed satisfies our conformal symmetry, right? I can even find it. So where we were. Yeah, just the same thing, right? In this case, again, our h is just 1/2 of scaling dimension because we consider scalars. So when we have something like z12, h1, z12, right? The holomorphic and anti-holomorphic conformal dimensions in the scalar case, they are the same. So when we have something like this is just z in the z squared in the power of h. So it's just nothing else but our combination of the powers that we just obtained. And that's, I think, where I wanted to finish today's lecture. So what we did is we established the direct correspondence between between SL2C algebra and Lorentz algebra, right? We talked a little bit about the adventures of Chewbacca and Han Solo as well. And importantly, we found our basis for celestial amplitudes. So we found our wave functions that that obey our conditions, highest weight, that are primaries. We derived the most convenient way of writing them down, which is the integral representation for massive and massless particles. And we even considered our first celestial amplitude that we met in the nature. So that's it for today. Tomorrow we will talk about symmetries on the celestial sphere, about how the Poincare symmetry acts on the state of space, about what are the generators, how do generators, which invariance we have on the boundary, which invariance we have in the bulk, and also which constraints on our celestial amplitudes we can obtain from the Lorentz and Poincare symmetry. So thank you for your attention, and I hope see you all tomorrow.